So I'm actually really glad that Alex preceded me, because he gave a great introduction to the field and also some ideas about how machine translation can be employed and deployed in real applications. And while my talk is going to be a bit more about surveying machine learning aspects, so how machine learn actually tasks, in particular machine translation. And if I want to, let me say, think about an analogy about how machine do, I can think about this example here of the Rosetta Stone, which was discovered end of 19th century. And what humans did actually was to leverage this parallel corpus here, because it's really a parallel text that you see, which basically covers hieroglyphs, Demotic Egyptian and Greek. And basically, by finding correspondent words in the two texts, they were able to decipher hieroglyphs. And this is what machines actually do, but on a much larger scale. So they actually are capable of ingesting and analyzing huge amounts of parallel data, and through machine learning algorithms are able to find connections between source and target sentences. And these ideas about how to leverage large amounts of data were actually explored first time in the late 80s by a team at IBM. And they had actually a hard time at the beginning. So this is I would say the first work about statistical machine translation, so data-driven machine translation, machine learning. They are all synonymous to me. And this was 1988, and they were able to publish. Nevertheless, they received very harsh reviews, and this is one of the anonymous reviews they received. The validity of statistical approach to MT was universally recognized as mistaken, and the crude force of computers is not science. Okay, so these were linguists, and there was really it lasted several, I would say, a couple of decades. I mean, hostility against data-driven language processing in general. So there were many linguists and influenced by other famous linguists like Chomsky that were not believing that computers could handle language just by looking at examples of data. So if I want to summarize what computers do when they perform translation, basically there are two aspects in mind. What you do is always to try to find a translation that is optimal with respect to some criterion given your source. So you're looking for the target with the highest probability given the source sentence, and you are performing this operator here, which is an argmax. So look among many possible translations, all possible if you can, and look for the one that improves your score, and finally come out with the best one. So you have a search problem, basically, which is how to efficiently generate, explore translation hypothesis, and you have a modeling problem, so how to score translation hypothesis, okay? So, of course, this is the most relevant part which I'm going to cover here, while argmax is basically about search algorithms, which are quite popular in artificial intelligence. So machines are not really, I would say, smart as humans, but they are faster in generating hypotheses and evaluating them. So we can directly go to the solution. Machines use a lot more of computations, but they can do it cheaply, of course. And what I'm going to talk here is about two relevant models, so ways to score translation hypotheses. It's phrase-based machine translation, which has been on the top system, the top technology until, I would say, 1.5 years ago. And it was the basic technology used by Google Translate, for instance. And what is the core idea here is that translations are basically produced by combining translation fragments. Okay? So hypotheses are generated by combining translation fragments, which are learned from parallel data, from data, actually. So if you see this example, our translation is basically a combination of a bunch of translation fragments, which are called phrases. Okay, so the difference with the new approach, which is called neural machine translation, which came out about 2.5 years ago, but really started to outperform phrase-based translation, is based on a completely different concept. So the idea here is that neural networks use some internal representation for the source sentence, and this is generated through an encoding process. So the input sentence is basically converted into a numerical representation. Okay, I wouldn't call it meaning. I just would limit myself to say it's an internal representation, numerical representation. So I'm using this, and even later, this level of grays here in place of numbers. People like more colors than numbers, I guess. So I would say white is 0 and black is 1, and gray colors are in between. Okay, so a second step then generates a translation hypothesis from this numerical representation, this internal representation. In this process is called decoding. We're going to see in more depth this approach. Now, if we think about how phrase-based translation work, we can start with another Rosetta Stone. Here it's just a piece of document from, I guess, the Europal corpus. So you have a version in English and a version in Italian, the same document. So the assumption that you make is that there is a 1-1 correspondence with, between sentences. Okay, that's the only assumption that you make. And programs, algorithms able to align at the sentence level corpora have been developed by the end of the 80s. And what they can do is, for instance, they can detect if, for instance, one English sentence has been translated into 2 consecutive Italian sentences, or 3, okay? Or vice versa. 2 English sentences correspond to 1 Italian. But the assumption is also that you can align so that it's monotonic. So there is no sentence that has been translated before another sentence in one direction and vice versa in another direction. Another aspect which is relevant is word alignment. So word alignment means trying to find correspondences between words, okay, in 2 parallel sentences. And this is technology that has been developed also at the end of 80s, begin 90s by the team at IBM. And this is a completely unsupervised process. So just by relying on parallel corpus, algorithms are capable of finding these word alignments, which are, I would say, prone to errors, but they're quite reliable because this is one of the building blocks used by phrase-based translation. The second building block is phrase extraction. So starting from parallel sentences which are word aligned, phrases can be extracted. The simplest phrases are made of single words. You look at the corresponding words and you get phrase pairs. So process is aligned with processo, and you can have this phrase pair, which is like a lexicon entry if you want. Okay, but you can work on larger blocks, and il processo di Bologna, the Bologna process, just by isolating a group of words that are consistent across the languages with respect to alignment. You can find many, you can find longer phrases, and so on. So you can collect many, many phrase pairs. And some of the phrase pairs are also overlapped. The important thing is that they are consistent with respect to alignments. And this process is applied to millions of parallel sentences, which make our corpora, like Europal. Actually, we have now available, since the beginning of the story, when the first experiments were run on the proceedings of the Canadian Parliament, which were in French and English. Now we have much larger parallel corpora, and from a variety of sources. Europal is one, from the European Parliament, etc. So it means that we can collect many of these phrase pairs, and the system can collect statistics. So it can it knows how often some phrase pairs have been observed, how often one phrase in Italian corresponds to some given phrase in English, and so on. So at the end, I mean, with this large collection, phrase-based translation basically uses a search algorithm that generates translation hypotheses, which are expressed as combination of these phrases, and evaluates translation hypotheses by computing different scores. So one prominent score is the translation model, which tells what's the probability of using this translation. So what's the probability of using Morgan as a translation of tomorrow, okay? Or Fliege of will fly. Another component of the score is the language model, which looks how well phrases fit together, okay? So how likely is that Fliege can follow Morgan, or Ich can follow Morgan Fliege, okay? It looks at the fluency aspect, I would say, of the translation. Another final important model is the reordering model, which looks at the order by which input phrases are translated, okay? So if you see this crossing here, it means basically that we have translated, we have applied some reordering, okay? So in the translation of tomorrow will fly, we are going to translate first will fly with Fliege with respect to I with Ich, okay? So this is a reordering. And this reordering model evaluates these jumps in position, okay? And these arrows corresponds, these different colors corresponds to scores or probabilities, okay? And these models computing these probabilities are estimated, can be estimated, learned from, you have a question?
Yeah.
Yes, please.
These three probabilities that we
yes.
are talking about are adjoint probability or three marginal probabilities that we are optimization each time?
No, these are marginal, so they are separate probabilities which are then simply multiplied together, or we take the sum of the log. And the idea is also to weight them differently, and this ends up with the so-called log linear model, which is, has been the state of the art for many years. So, but what I want to say is it's a combination of scores. And to me, it seems like when in computer chess, okay, computer explores with a search algorithm different moves, okay, and each move corresponds a new position, and the position is evaluated by some models. And the position takes into account many things. It takes into account how the king is protected. It looks about how isolated are your pieces. So you cover many aspects, and you combine all these aspects into one score, which gives you the goodness of the move. And here you have basically scores giving you the goodness of your translation hypothesis. So there is a quite similarity. There's quite a similarity between the approaches. Okay, now let's go to neural machine translation. As this is quite new in terms of concepts, I mean, Alex gave a nice presentation. I try to complement what he gave by telling you a bit how neural nets actually works. And I'm using a simple task, which is image classification. Oh? Okay, I have a neural net which is called feed-forward network here, which means that the network basically processes information in one direction, so from the bottom up. Okay, and the idea here is that we use this network to perform image classifications, and we have images in input and we have classes in output. Okay, so we have 4 classes here. We have images in input, and we have to map them either into dogs, cats, owls, or lions. Okay, we have to tell what the image in input is. It's a tiny example, but keep in mind that even bigger networks work exactly in the same way. They have just more nodes, more connections, but the principle is the same. So our assumption here is that we start from some input, and the input is numeric, and here I'm using colors again, and you see the connection, the correspondence between colors and numbers, okay? And my assumption here is that this is the image of the cat. Of course, You can think of gray levels, image in gray level, a much larger image, but I want to have a smaller picture, so we can assume that we can squeeze our kit in just few numbers, okay? But you can imagine that these are many more. So let us see what a network does, actually, and it's quite simple to understand, okay? The information that you have in input is going to be processed by the nodes at the next layer, okay? And all these nodes basically do the same kind of operation, so we just focus on one of them, okay? So we focus on this node, and this node basically, what it does is something simple. This node has some connections, some links, some arrows arriving, and these are, they own some weights. There are some weights corresponding to these weights, to these arrows, to these connections. And there is also a special connection with a bias which has its own weight, which is -5, okay? So what is done is simply multiplying the inputs, okay, with the weights and taking the sum, okay? So you multiply this by this, plus this by this, plus etc. Plus 1 times -5. The sum gives you 2.7, okay? So it's not about meaning here, it's about what is performed. 2.7. This 0.7 is passed through a sort of, it's a special function called activation function, which is called also, squash function, that basically maps the range of possible numbers, which is between -infinite plus infinite, in the range of 0, 1, okay? So it's a squash function. So large numbers are mapped into 1, and very low numbers, -10, are mapped to something close to 0, and intermediate numbers are mapped between 0 and 1. That's it. So it tries to keep the things between the range 0, 1. Okay, all the nodes, the remaining nodes, the siblings here, do the same thing. The only thing that difference are the weights. So each of these nodes has its own input connection with its own weights. And this produces different results. We had here a value, I don't remember now, it was 0.94 for this node, but here we can have different values, okay? Now, next level, same thing, different weights only, okay? And you go on up to the top level. Now, how you interpret the top level? The idea is that each of these nodes corresponds to a class, this all, for instance, and we see that the network prefers the class with the highest score. Okay. That's it, okay? So in this case, we have the best one is here, and this is the class that wins, okay? Networks basically are defined by an architecture, a topology like this, and weights and biases, which are numbers and are our values that we connect to the network. So once the architecture of the network is fixed, its behavior only depends on the values of its weights and biases, okay? So how do we learn them? So we start with some random weights and bias and progressively adjust them by trial and error, okay, over a labeled data set. So we need a labeled data set. A labeled data set is something like this. So we have for each class, okay, we have examples, okay, correct examples. Ideally, we are going to split between training and test, the data into training and test. So we're going to keep something out from the training data, okay, for verification if we have learned something. While we are using the training basically to learn weights and biases. And how we do? So we start with a random example for which we know, of course, the class. So we have an example of all. And we let the network compute the output with some random weights, okay? Our initial guess of parameters. And we get lion as the highest class. This is an error because it should be an all, okay? So with an error function, we compute an error, and through an update function, we compute an update, a modification of the weights, okay? So that the error decreases, okay? So we update the weights, and with these weights, we perform another iteration. So we have another image, a lion, it's misrecognized as a cat, it's a lion, error, update the weights. And we go on. It's a dog, another error. So after many, many iterations, the network can do this very, very quickly. So we come at a point in which we have a dog. Wow, it's dog. Error function tells it's 0 error. We are done. Okay, so or we are in good shape. You want?
Can you difference severe and minor errors in the system? Severe and minor errors?
No, it's
linguistic based now.
No. It's just now images. It's just really errors related to the output. It can be 0, 1, or the amount of probability. I mean, you have some more fine-grained error functions, but the real point is just 0, 1 here for the moment. Okay, correct, incorrect. So we could think, okay, we're done. Let us try on the test set. Okay, we cross-validate our network on some data which has never been observed. Okay, so we try with the cat. Oh, it guesses the cat. It's good. So we start to be happy. An example of all, we get correctly an all, and more positive, we have a dog which is recognized very well, and we are going to really finish our stuff. Then we have this example here, and this is it's a very young lion, okay, and we get cut here. So there is a mistake. So what I want to say is that there can always be for a network examples for which you get some bad behavior, just because the network learns just from the training data, okay? It tries really to optimize performance on the training data. Of course, it has a generalization capability, but you are never sure that something strange can happen, okay, that you have not covered well in your training data. There is a nice example because even with networks which are much bigger, more complex, trained on large amount of data, you can see some strange errors like this one. Is it a muffin or a chihuahua? So, I mean, if you look at these two examples here, you could have some doubts. Okay? And you can imagine this can happen for text as well. I mean, whatever you try to train with a network. So it's really about coverage and quality of the trained data that you're using. So mathematically, I don't want to bore you, but everything has a mathematical framework. Training sample are couples here of input-output. You have your model that does predictions. This prediction depends on the parameters. You have a loss function that computes the errors, and you have your training criterion, which tries to minimize the loss function over the whole training data. And what you do actually with this trial and error is basically try to minimize the loss over your training data by using a gradient optimization method. And so every time you're computing, estimating a gradient of the error and moving in a direction that gives you better performance, okay? And this is the principle. Now, we are talking about text here, so these neural nets that work well for images do not fit for text. For the simple reason is that images have a fixed size, text can have a variable size, okay? So the text are sequences. So the way we process sequences is with recurrent neural nets, okay? And here I give you an example of simple recurrent nets. So at first glance, which difference you notice with respect to the previous? Because the number of layers is exactly the same. One thing changes.
The arrow will go back to the sequence.
That's correct. So you have connections of this layer with itself. So each node is connected with all its siblings and with itself. Okay? So this makes a network recurrent. It means that over time it can process information over time and remember its states in the previous for the previous inputs. The way we pass input to this network is also different. We used images with levels of grays. Now we use so-called one-hot vectors. So it means that for each of these words, input nodes correspond to a word of the vocabulary. So on, mat, cat, is, the, sleeps. It's a very small vocabulary again. It's a tiny example. And when I put 1 here, it means that the input is the word the. Okay? And the word the is the number 1 here for this position. And the processing is exactly what I've shown you for the image network in every aspect. Maybe the only thing which differs is this self-connection. And in this sense, it makes more sense to see the network represented in a different way, this one here, okay? I think it's not difficult to see that it's an easy relationship. The only thing that I omit is all these net of connections here. I just put 1 here, so I make it simpler. But there is this connection here, which is used to represent the connection of the layer with itself. And here you see an example of sequence, the cat on the mat, okay? And here you see the processing of a sequence. So first, the gives you this representation here, then this is passed to the network for the next word, okay? So that this layer here uses the input from this layer and from itself in the previous instant, for the previous word. And this is how you process a sequence with this network, okay? And this is called time-unfolded recurrent net. It's one aspect which is interesting and can have some intuition behind, is that the first step, which goes from the 0, 1 vector to the first layer here, this continuous representation, these are numbers here, is that this represents the so-called word embedding. So it basically means mapping words to a continuous space, and here I just make a simple representation in a bidimensional space, okay? And what typically happens with these layers is that words which are similar in use, semantically similar, are mapped to closer positions, to close positions. So what you will find is that for an application with a small vocabulary, that the word cat, cats, kitten, will stay close together in this space, okay? So this is one of the operations that the network does. Now, let's go to the real neural net that does machine translation, neural machine translation. So we have 2 networks, actually, an encoder network, which you see here, which basically has input layer, then embedding, and just 1 recurrent layer here. And this can ingest an input, okay? The cat on the mat, okay? And what we say now is that this node here, basically this layer here, contains the information of the whole sequence, okay? Because you see that the content, this representation here, depends on the last input, but also on the input from the previous word, which itself depends on the input of the previous, etc., etc. So this one, in principle, can accumulate information of all the previous words. And we can think that this is the representation of our input. Yes?
Sorry for the question. So this is the same way the previous presentation
yeah, encoder, decoder, yeah.
it lost positional dependency.
No, this has... No, here, this is a sequence. Position is used.
Yeah, the output is not positional dependent.
No, the output has some position dependency. Yeah, because sequence matters here. The order matters. Yeah. So encoder final state represents the whole sentence. Okay. Now we have a decoder now, which is another neural net, which has another purpose. This one has the purpose of storing the information of the input. This one has the goal to produce a translation. So what it does, it's a network that basically is capable of predicting a word in the target language. And you have to give a trigger word, so basically the previous word, and we start with an initial start symbol here and say basically, okay, please predict us the first word in the translation. And the first word in translation is predicted by using the input here, as input the state of the encoder, and what it does, it has an output layer which produces scores for each word in our target vocabulary. So in this case, we look at the scores, and the highest score is the word ill, okay, which is output here. And this word, okay, is used as input for the next step. So we query every time this network by asking, okay, give me the next word, give me the next word, okay? From ill, we have gatto, and so on, okay? So every time that we do this prediction, we are using also the final state of the encoder. Yes, please?
Sorry, for the loss function of the first neural network, which labels we use to train the model?
For this one?
Yeah.
Yeah, what we are using are exactly translations here. So these are our labels. So it's exactly the same principle, and now labels are words, okay? So while we are training, we are providing as label, if the correct word was ill, okay, in our train data, we would have 1 here and 0 on all the other words. So we try to force the network to learn to produce ill as a first word.
And for each sentence, we have to train the model because it's for the recurrency?
Yes.
Okay.
Yes, yes. Oh, and you have millions of sentences.
Sorry. Does
Yeah.
it work well also with the language that are different in forms of sentence? Something like English and Japanese or Chinese?
Most of the gains have been achieved on languages like Japanese, for instance. Yeah. Okay, I was at this point here. So there is an issue. The issue is that networks tends to forget. Okay, so taking this representation here for the whole sentence, that didn't look a very good idea. So what was proposed successfully was to use something called attention model, and we are going to have a presentation after me about which is going to be all about attention models. Okay, so when you see these boxes here, it means that every time you produce a translation of one word here in the target, you are querying the attention model. Okay, and what is the attention model helping you? So the idea is that the attention model tells you which is a good input state for the current word to be predicted. So here, for instance, to predict the word after ill, in my translation, the attention model tells the decoder to look at this state here. So intuitively, it does something like the alignment model did. You remember the alignment that gives you the correspondences between words? So it predicts you where to look at, okay, among the information produced by the encoder. So we store all these states here, we make them available to the decoder, and the attention model will direct the decoder to the right encoder state when it has to translate. And this provided quite a boost. Another boost comes from processing in two directions the input, so from left to right and from right to left, and use two different encoders basically that produce sequences in reversed order, and basically use both these states as information. And the reason is quite simple if you think. These states here basically store information of the current word and of the previous word, while this state here stores information from the current word and the next words. So you basically have a sort of representation of the word with the context. Okay? And the idea of using attention model is that you cannot let the context grow too much. Okay? It's better to keep it local. Okay, there is another step, I would say not very important too, is to replace these simple self-connecting cells that you have seen at the beginning with something more complex. I don't want to go into the details, but these more complex cells are more effective in storing and propagating information. So they work more effectively, but this is a detail. I think the concept really is behind the important concept is already been stated, and it's this recurrent net. that can process information over sequences. So what about the quality of neural MT? So we have been several evaluations. We run one based on human assessment, and in particular by human translators. So we asked professional translators to fix translations of neural machine translation and of top performing phrase-based translation. So to make a long story short, we found that neural nets improve over several aspects. Lexical choice, morphology, okay? We translate here from English to German, so morphology matters. So we found improvements around 70% and 90% of lexical errors and morphology, so better word rendering. But what we found surprising is that it basically cut by 50% word order errors. So it's much better in coping with the infamous problem of finding the right position of the verb in German, especially when you have these passive constructions, and neural nets are much better in placing the verb in the right place. Okay, I want to compare now. I want to look about how well and how they learn machine translation. So phrase-based and neural MT learn differently. This is important. So I look at two dimensions, memorization and learning here. So memorization, basically, in the extreme case, 100% memorization means just memorizing the training data, okay? And this is what, if you think, if you are in the translation business, is what translation memories do. So translation memories are basically memory storage of all the translations performed by translators, by translation companies, etc. So it are just data, okay? And translation memories, we can think them as a rudimental tool, as a rudimental machine translation engine. And actually, since, let me say, a few years ago, professional translators were just using translation memories as a tool, okay? This is 100% memory, I would say. They are not able to learn anything. If you provide a new translation, a new input never seen, they are not going to produce a translation for it. They're just doing something different. Phrase-based is a combination of memorization and learning, because phrase-based memorize translation fragments, and translation fragments can be of arbitrary size. So in principle, they can learn the whole training data, but with small fragments, you can build new translation of new sentences. So you can generate new translations, okay? So you have a good component of memorization and good component of learning how to perform new translations. Neural MT is a step further in learning, and it's a bit behind in memorization, okay? Human translation is even further. So we are bad at memorizing all the translations, but we are good at generating new translations, okay? Now, from a machine learning perspective, let me think that translation is learning a function, okay? A function that maps French sentences into English sentences. And please, try to believe that we can map sentences in our space here as points, okay? As dots. So we have training points, training data points, observed translations, and testing points, which are new sentences, okay? And these are the translations of the. Now, if you look at the differences of the approaches, so translation memory can be seen as a nearest neighbor machine learning algorithm. So find the nearest known example to my input. So a translation memory does exactly this. It looks for the most similar input, source sentence, okay, and returns you its translation, okay? So it basically can only return you training data points, okay? And this means that you make systematic errors on the test data, okay? So what I'm showing here in this line, corresponds to the translation that is given you by the translation memory for each of these white points. Okay? For this point here, it's going to give you the closest translation, observed translation, which is this one. Phrase-based performs a sort of interpolation. It builds, for these white points, it tries to build a translation by combining fragments of the similar translations. Okay? And this is how it generalizes. It can find translation for this point. It can find a translation which is here, which contains pieces of these and pieces of these. Okay? And this is the concept of phrase-based translation. Neural MT does something completely different. It tries to fit the training data with some continuous function, like this. And this is why it can perform quite well on the test data. It can provide quite good translation on the test data, although it could not recall properly training data points. So if you provide an input for these, if you train a network and provide the input of this translation, it will give you this translation, not exactly the one observed in the training data. So it cannot typically reproduce the training data. We run experiments on data which contains many information sources, I would say 8 information sources. So different domains, we call it. Technical documentation, legal documentation. So we train a network in a multi-domain setting. And in a moment I tell you why. And we tested it by looking also at the performance of each translation with respect to the similarity of the source with observed training data. What does it mean? So if you translate with, here we have translation memory, okay, which is this yellow. So test data, which is very similar to the training data, is translated perfectly. And here we are using blue scores as a measure. The higher the score, the better the translation. Okay, if the source has a similarity of 0.4 with respect to the closest training point, you have performance which is quite low. Okay, while phrase-based translation is better than neural machine translation. So neural machine translation works well when you have low similarity between test and training. Okay. And typically, if you are translating news, for instance, there is less repetition with training data. So you are always in this area here. Neural MT works better. If you translate Wikipedia text, is the same. If you're translating technical documentation with a high degree of repetitiveness, phrase-based outperforms neural because it can recall very well training data. Please. Yeah, it's a similarity measure.
Yeah, okay, so in the narrow machine, so narrow-based network for translation, they don't have this, so they can change the word.
Yes, it's correct. Yeah, there is. So that's a good point. So it's questionable if to use this kind of. But let me make the assumption that we have technical documentation and that terminology is relevant, and it's good to adhere to the references. And here we are measuring the adherence. And I agree with you that it doesn't mean that translations are bad. They could be good, but they adhere less to the 5 minutes. Great. So what changes is that let us think that neural nets now can be adapted or specialized to a particular domain. So we take the generic network here, trained over 8 domains, and we train 8 different networks, okay, each specialized on each single domain. So if you specialize networks, you are doing the best, okay? And this is because if you specialize networks, you increase the memorization power of the network. Yes?
What does it mean to specialize the...
Specialize means I take this network here and then I retune it just on the data of each single domain. So I force the network to observe only data of that domain after a given period. So it means that it concentrates very much on the sentences of this domain and becomes better in that domain and worse on the other domain.
The domain knowledge, the domain of
Yes, correct. The domain of the source. Yeah, and this is we call it customization. So domain customized neural nets are the best solution. But it's not a scalable solution. It's expensive because you should have one network per domain. Yes.
Is it as well terminology training?
Yeah, we assume that in the training data there is also terminology. We can use also terminology as training data just by adding a lexicon with all the training data. Okay, I'm quite over, so I give you just some bonus slides about hot topics, but I'm over. So what we're working on is real-time adaptive neural machine translation. So we have different domains, okay? We have one generic network, and our idea is that we could, on the fly, on demand, adapt it on a single sentence, okay? And if we can do it very quickly and can get better performance, basically, by this on-the-fly adaptation of sentences, so that we can have the advantages of customized systems and generic systems in terms of quality and cost. And this is recent work in our lab. Vocabulary coverage issue is another aspect which is important. We have these 0-1 vectors. We cannot have, we have to keep the vocabulary under control. So the idea is that we use subwords instead of full words in our vocabulary. And subwords are automatically generated from statistics. So for instance, shipping was delivered timely is going to be split in these components here, in subwords. And subwords basically allow you to keep the vocabulary size under control, okay? We are working on morphologically consistent subwords, which work quite better, especially for agglutinative languages like Turkish, in which if you look at the BPE, so the subwords automatic generation, it can give you it can screw up the meaning of the words, basically, because the word kaunda, if split in this way, it generates a root for blood, which is very different from the original meaning, which is in the law. Okay, there was kanun inside, which is law. So what we try is to use segmentation that takes into account morphology, that doesn't screw up the meaning of words. There is work on architectures, so deeper architectures, many layers. This is the architecture of Google of last year. This is the architecture of Facebook published this year, which is based on convolutional nets. And this is an architecture which does not use any more recurrent neural nets, okay? There is the architecture which is going to be explained later by the new one by Google. This is another architecture produced by, found out by Edinburgh University in the UK, which is also very interesting. So combining deepness or depth of layers with particular kinds of nodes. So making networks deeper allows better performance because different layers can cover different aspects of abstractions of the representation. 1 minute. Okay, reinforcement learning is another interesting area, and this is borrowed from robotics. Okay, so robotics can learn from the environment by performing actions, okay, and receiving feedback from the environment that tells, okay, you were successful, you were not successful in this operation. And from this feedback, they change their internal policy, okay, for performing actions. And the same principle can be brought into neural machine translation, okay? And basically to learn from feedback from users, from weak feedback from users, for instance. And this is where very, very interesting area. So conclusions, neural machine translation opened a new era, and we are living really turbulent times because every 2 weeks there is some new idea, something that makes you doubt that you should change your models because someone else found something better. So we are getting very powerful tools because many labs are producing open source code software that you can use to develop neural MT systems. And I guess it will take some time now to get the full potential because we are really still in the hype, I would say. So I expect we will see lots of changes in the future. And I thank you for your attention.